So thank you, everybody. Thanks for the all of you with the great talks before. And actually, Roy talk is very related to mine, so it's a great build-up. Yeah. So hi, this is a true story about detecting malicious storylines. I'm going to show you how SentinelOne using smart context called storylines to try and detect malicious activity on the endpoint using machine learning. So just a little bit about myself. This is my gang. I'm Braun. I'm father of two, married to a D. I'm a data scientist in SentinelOne for the last 5 years. I'm working on my master in software and information system engineering in Ben-Gurion University under the supervision of Professor Lior Rokach. And I'm very interested in the field of representation learning and adversarial attacks. So if you want to have any chat about the subject, feel free to drop a private message later. So SentinelOne, the company established as what called a next generation antivirus, which was focused mainly on endpoint protection on all the main operation systems. We have different products like static file AI detection, network visibility, XDR, and cloud intelligence. We are basically collecting data from different sensors and indicators from our customers' endpoints about what happened there from the endpoint servers and also the network to try and detect malicious activity, which we will call threats. Above that, there are also different kinds of services like our MDR, which is very similar to what we called as a SOC, which is a service of security experts that sits inside SentinelOne and can manage customer sites if they want to. So as part of SentinelOne products, we don't just try to throw machine learning on everything, but when we when you use it, let's discuss on several examples of possible goals based on data that we're collecting from our customers. So the first one is new threat detection. So by giving the whole data from a customer, we want to detect some, if there was some attack without any prior alert or a hint that something fishy is going on. The next two goals is some enrichment task above a known threat in the system. So SentinelOne got, as I mentioned, different sensors that can raise different flags for possible threats. And by assuming that we know we have a specific threat in a customer, we can try, for example, to achieve threat attribution, which means we want to discover who is the attacker. Another task is to classify whether a raised alarm is actually false. I assume that we all know that the world is more complex than our labs. So we could try and use real world data and past examples that we already classified incorrectly to reduce our false alarms. So the final goal that I wrote, I wanted to share, is that based on our data, we can also try and profile different entities in the systems, like users, machines, and even the whole customer to try and find activity that is unusual to relevant entity. So because lack of time and relative lower complexity of the task, I want to focus on classification of exist threats, which mean we know there is some suspicious activity, some sense of sentinel alarm, and we want to know whether it's a false alarm or a real threat. And I want to take you through the adventure of how the thinking process was to create this kind of solution. So we know what we want to achieve. So let's understand what is the nature of SentinelOne's data. So we stream different kinds of data sources like logs, telemetries, and files. And one of them called deep visibility, which is our EDR solution. EDR is abbreviation for endpoint detection response, which means basically given a customer computers, we have our agents on the machines, and that sends data to our cloud infrastructure, and eventually the data is aggregated and accessible for the customer security experts to see it in a convenient UI to easily understand what's going on in the network. So our EDR solution, as I mentioned, called deep visibility, and here's an and here is an example of data you can see there. For example, you can see specific endpoints had specific processes and executed specific command lines. For example, you can see a WinWord executed some command lines in some endpoint, and the analyst can write complex queries on it and to find interesting stuff. Also, you can have a deeper drill down to see the whole relevant storyline and which are the communicating entities in the specific case. But of course, we are interested in the data itself. So here we can see how the basic form of the this data hidden behind the UI. We have the event type, we have the source of the event, the target of the event, and some different properties regarding the event. Also, we got a storyline ID, which is the context of this event. After mentioning it like several times, let's talk what is a storyline. So our agents, after logging all of the actions that happened, also segment the events to different contexts, which these are the storylines. In the case of some incident happened, which will be possible to understand exactly what was the problematic processes and remediate them in one click and roll back to a normal activity. So for example, just to understand exactly what is it good for, if you have a setup.exe file that was downloaded by some user and was executed, we can see that some processes was spawned from it. And also there was some winword.exe process that also spawned a PowerShell script. Let's say that our agent detected that this PowerShell script is malicious. We understand exactly what caused the threat. And in this case specifically, we know that winword.exe is not malicious. We don't want to delete it and prevent from the user to use Word documents in the future. So, excuse me, probably just document some document that executed a macro that caused a malicious activity. So back to our data, we said that our mission now is to understand, given a threat that was raised from one of our indicators, whether the indicator was right or wrong. Or in other words, whether this whole storyline, the context of this action was benign or malicious. So each one of our storylines is actually the sample of our data and is a table of deep vis events that represent a full storyline from one of our agents. And we want to train a classifier for them. So our raw data contains different kinds of data types, like events, OS, or permissions can be represented categorical data. File sizes and action counters can be considered as numeric data. Time differences, for example, how much time passed from the process start until the current event. And even textual data like command lines and file paths can be used to understand better the nature of the activity. So we have some data extracted features, and we mentioned we want a classifier for our storylines. What about some labels if we want to have some supervised model? As I mentioned in the start, we have an MDR service, which is called Vigilance, which is constructed from security experts that responding to threats raised by SentinelOne's agents. So basically, they go over a long list of threats and handle each one of them. If it's a false alarm, so maybe unquarantine the deleted file or a rollback if needed. If it's a true positive, real malicious activity, they're following the case and checking which actions need to be done. And as a side product, we get labels. We are using vigilance decisions on our storylines to understand which past alarms and this specific context was true or false. So of course, it's not that simple. We have many challenges in that area. For example, what part of the storyline caused it to be malicious, what can be, it can be many reasons, it can be different events inside of it. There's the whole issue of opposite labels for very similar cases. And even more extreme, there's like a whole category of processes that called PUP or potentially unwanted programs. That, let's say a customer doesn't want the employee to be able to install games in their laptop and consider the activity of a Steam.exe as true positive. But other customer complains on false positives on Steam.exe because the exact same behavior, because they don't care if the employees will play games on their own time in a weekend. So I won't talk about the solutions here, but just want to emphasize that it's pretty complicated situation. Okay, so we talked about now about the data itself, the raw data, before transforming it to different formats. Let's talk about some of the methods that we tried to apply to achieve our goal. So the first thing is to consider a storyline as a tabular data. We have this set of tables that we want to create some vector features from each one of them. So for example, we can take each one of the table of events and try and use manually engineered features. For example, how many processes was in the storyline, how many files was touched, what is the average command line length or entropy, did it contacted any external IP or a lot of internal IPs, and so on. Those features are thought together with security experts to try and understand when an analyst sits on the console and decide if a storyline is true or false, what he thinks triggering his thought to this direction. So we end up with some manual engineered vectors of features per storyline, which we can use in any of your favorite classifier, like boosting trees algorithms as XGBoost or CatBoost, neural networks, or any other preferred classifier. This method from one side is very easy to apply, but unfortunately, we need first thinking about what are the features that are interesting. And also we lose a lot of important data that come from the unique structure of the storylines. So the second approach that we wanted to try is to consider the storyline as a graph of entities. So here on the right, you can see a storyline that I used bokeh to visualize the graph. Here, each circle represents some entity, like a process or a file. And each line between those entities represent an event. So for example, these green lines here are files and the orange ones are processes. And example for events, possible events would be like process creation or file modification or file deletion, registry keys, modification, and so on. So as you can see, it's very intuitive to represent the storyline as a graph. Most of the entities and connection definitions already exist through our deep visibility data nature. So we need to decide on interesting information and the method to process the graph. So as I started to do a simple research on the whole graph classification task, one model that seems to me simple to start with was a method called graph2vec, which is basically doc2vec for graphs. A reminder, doc2vec is an extension to word2vec, which I assume that most of you familiar, at least in basic concepts, used to extract word embeddings. So doc2vec adds a second matrix that will represent documents representations in a new latent space and will be optimized during this training. So the authors thought about the idea that a graph is constructed from subgraphs in a similar way that a document is structured from word. The author used a tool called Weisfeiler-lehman kernel to achieve the task of indexing subgraphs. So what is this thing that sounds horrible? So how it works? We have here two sample graphs, which we want to understand their internal structure and decompose it to subgraphs. We can see that each node has some label. So in our case, each one of these labels can be, for example, the type of the entity, like the 5 can be a process and 2 can be a file. And the basic idea is that each node will compute new label that will represent its neighborhood. So as you can see here, these 4 had a neighborhood with 1, 1, 3, and 5 labels. And now after the first step, it's changed the label to this concatenation of labels. Interestingly, to see, for example, that this 5 in these two graphs has the exact same neighborhood and the same labels. So after the first step, they got the exact same representation. The rest of the graph doesn't affect. So next, the new neighborhoods get new labels. And we basically can do this process again and again to represent neighborhoods from different depths. It's some hyperparameter that we should optimize to each one of the cases. So finally, what we can see is some representation of a graph that is a count of the original labels and some new high-level subgraphs. And this is basically the unique identifier for the graph that we can use for the embedding process. Okay. So here you can see a result of representation extraction that we did in one of our iteration, reduced to 2 dimensions. The orange dots are false positives and the blue dots are true positives. So yes, the results are far from perfect, but we can see there are many places that we got mixed labels, but also there are some places, clusters, that are pure unique, and we can use it like in classification or clustering method to try and classify some of the data. So after deeper thinking about this subject, I got to the conclusion that using Graph2Vec to the specific project will be suboptimal. It got me to understand that this might be a good direction. But firstly, the algorithm is transductive, which means if I get new graphs, I need to retrain all the embeddings from the start, because as I mentioned, the subgraphs is similar to words. So it's and graphs are more verbose and it's more sensitive to out of vocabulary problem. So and with latency of training this process again and again, it was not good enough in our scenario. Secondly, the Weisfeiler-lehman kernel, working, as I said, with a single label. We saw each node got a specific label, which in the case I showed earlier was the type of entity. I already thought about like there's a lot more information like command lines and times and counters, as I mentioned. It's pretty limited here, and we should like think on something more complex. So both of the issues can be solved with some complicated settings with Graph2Vec, but I decided to search a different way. And then I got some revelation. A different popular approach, which gaining a momentum in recent years, what's called graph neural networks. There is a lot of theory behind those models, and there are countless variants and papers that suggest new architectures, but let's just go over the main concepts to understand why we chose it. GNNs trying to do for graphs exactly what two-dimensional convolutions and pooling layers did for images. Basically, we want to understand for each node and edge what the attributes of the neighborhoods. So which sound very similar to what Weisfeiler-lehman kernel trying to achieve. So one of the more popular methods called a message passing, which basically each node contains its features and propagate it to the rest of the node every step and update its internal data based on messages it gets from its neighbors. So slowly through several layers during training process, as a regular neural network, we update the model to understand which connections and internal features in the edges in the nodes will be more important to reduce our loss function. So as I said, the process often called message passing, and it's constructed from two basic steps, aggregates and updates. So just to have a little bit of understanding of the concept, let's look on a few definitions. So let's say we want to calculate the new hidden state of node V in layer L. First, we want to collect information about the neighborhood of node V. So for every node in the neighborhood, every node U in the neighborhood of V, we want to aggregate their messages. So let's define what is a message. So the general, more generic explanation of what is a message can be defined in many ways, but it's some aggregation function that receives three values: the last hidden state of node V, the last hidden state of node U, and the last hidden state of the edge. And after we have aggregated the states from the neighborhoods of V, it's time to update the representation. Okay, again, there's some function that receive the last hidden state of V, and the aggregated messages from its neighborhood and some update function. So this is all I'm going to speak about GNNs, pretty short of time, but I highly recommend you to read about it. It's shown very effective. It has its like difficulties, sometimes like different graphs. If you have very large graphs and small graphs, it can be like not symmetric, the training time. But it's very interesting. So the last method I want to mention before I wrap it up is considering the storyline as a sequence of events. So for each one of the events, we will also have a timestamp. So we can consider each one of those events as a token that we need to understand how to tokenize it like in a proper way, but we can try and use it to classify the storylines. I won't go deep on what we tried here, but we need to do like different adjustments, but basically we can use each one of the known models for sequence modeling, like RNNs or transformer variants. For example, we can try and use masked language modeling like BERT to try and predict a relevant event. So a summary, as I explained about a little bit about SentinelOne's data, explained how we use complex context to have better understanding of the connections between the different events in our data. For the application that I mentioned here, we start constantly fresh labels with the help of our security experts in vigilance. And finally, we try to use different approaches and models to achieve our goal. And that's it. Thank you for listening.